Welcome back to our video tutorial. In this one, we're going to look at the solutions for Skill Sheet 6.2, friction. Please remember to pause and rewind the video as needed. Now, as you recall, friction is a resistive force either to motion or the attempt of motion. Now, there are two types of friction involved. Okay, static friction prevents motion. Sliding friction, otherwise known as kinetic friction, is the opposition of motion. A couple of variables you're going to need to know when you do your work. Okay, number one, the friction variable, which has the unit of newtons, is the lowercase f. N, the normal force, also has the unit of newtons. And mu, this little variable here that kind of looks like the letter U with a kickstand out in front, this is the Greek letter mu, and it stands for coefficient of friction. The coefficient of friction is going to be a unitless decimal in the answers, and it is going to range from 0 to 1. So it'll be a unitless decimal somewhere in that range. Okay, the closer you are to 0, the closer the situation is to being completely frictionless. The closer to 1, the rougher the two surfaces are as they contact each other. Now, if we take a look at an object moving on a surface, this is, by the way, the exact same picture you're pretty much going to draw for every diagram. So in the given box, I want you to get used to drawing a picture so you can see how the forces interact with each other. Okay, you're going to draw the weight. Well, actually, yeah, we're gonna get practice sketching it out. We got the normal force coming perpendicular from that surface. You have an applied force either to move it at a constant speed or to get it moving, one of the two, and you have static friction. You have friction, which is equal to mu times normal force coming out the other side. So this is going to be our standard picture that we're going to have for every scenario that we work. So if you want to copy it, kind of like I'm doing, we'll just sort of paste it where it belongs. Okay. All right, let's dive right into number one. Read along with me, please. Huge pile of leaves was wrapped in a tarp in the middle of the lawn. The wrapped leaves weigh 580 newtons. The coefficient of friction for the lawn is 0.55. How much force is required to start sliding the wrapped leaves? So first thing I'm going to do in the given box, I'm going to paste in my situational force diagram, because that's going to allow me to see that the normal force always balances the weight. Okay, that's what I know in my formulas here. I know normal force equals the weight, and weight equals mg. So that's one equation I know right away. The other one I know is that the applied force to get something moving balances friction, which equals mu times normal force. So applied force equals friction, right, which is equal to mu times normal force. So these are going to be pretty much the constant set of equations we're going to use in various points. Now we're looking for how much force. So you can see that's a horizontal force. We're really looking for friction. So the normal force is equal to the object's weight. Okay, so that's the first thing we're going to do is we're going to find the weight. Let's find the normal force, which is the same as the weight. Okay, now I kind of jumped the gun here with an mg calculation because I'm just so used to doing that, but I forgot that in the problem we were given the weight of the leaves as 580 newtons. So we know the normal force is 580 newtons. Okay, so now The applied force is the applied force going forward to get the bag of leaves going is the same as the friction that's preventing the leaves from moving in the first place, okay, which is your mu times normal force. So that's what we're plugging into to finish and solve this. Mu, that's this number here, the unitless decimal you see, 0.55, times our normal force, 580 newtons. And let's go ahead and please take a moment to put that in your calculator. Need some of that. Throw that up top here for when I need to use it. In fact, actually, let me go down and just go ahead and move that to each question. Just kind of take a second to set that up. And then I won't have to do that later. If we multiply 0.55 times 580, you'll get about 319 newtons. Okay, let's read number 2. Although the Collie Lassie could easily pull the 110 Newton empty sled empty, she could not even budget with 380 Newton Timmy aboard. How much force would Lassie need to apply to the slide with Timmy aboard, assuming a coefficient of friction of 0.15? Well, you should see that number 0.15 is very close to 0. That means it's not a whole lot of friction to get this thing going. But still, the heavier you are, the more force required to budge something. Okay, so let's put our picture in there. This is going to be kind of our standard picture every time. Now, the weight we were told in this case is going to be the sled plus Timmy. So you got to add those two together. Okay, so 110 newtons plus 380 newtons, right, is 490 newtons. So we need that. And then, of course, the normal force equals the weight, which is also 490 newtons. Okay, so in our equations here, our formulas, right, normal force equals weight, applied force equals friction, right, they're balanced, which is equal to mu times normal force. Okay, so we're looking for how much force? So F, right, equals friction, which is equal to mu times normal force. Let's go ahead and plug into that. And we know that mu in this case was 0.15 with a total normal force of 490. Go ahead and take a second to multiply those. You should have gotten about 73.5 newtons. Okay, number 3. A plastic wading pole weighs 50 newtons, but with the water in it, it weighs 4,000 newtons. How much force is required to slide the pool if the coefficient of friction is 0.22? Similar idea with the sled and Timmy and the dog pulling. Similar idea. The total weight, right, is going to be your 50 newtons plus your 4,000 newtons, right? Or 4,050 newtons. Keep that in mind. Your normal force, right, is the same as your weight. And applied force, right, balances your friction. So normal force balances your weight. Applied force balances your friction, which is equal to mu times normal force. Again, we're looking for how much force. So we're looking for F. So F is equal to the friction, which is equal to mu times normal force. Okay, and the mu, right, was 0.22, and then the total normal force that must be overcome, the total normal force acting from the ground, is about 4,050 newtons. And so in order to move the swimming pool with water in it, you have to apply a force greater than 891 newtons. Number 4. The boys pushed and pushed. At an applied force of 804 newtons, they were just able to move the 1,340 Newton car. What was the coefficient of friction? Okay, so this box right here represents your car. Okay, so they pushed with an applied force. What are they given? They were given an applied force of 804 newtons, which is the same as the friction, right, that they overcame. So the applied force is the same as friction, which is equal to mu times normal force. We are given this right here, which is the weight of the car. 1,340 newtons is the weight of the car, and normal force balances weight. You're solving this equation for the coefficient of friction, which would be mu. So I know that force equals friction equals 804 newtons. I know that friction equals mu times normal force. And in order to solve for mu, I have to divide by normal force. So mu is equal to friction divided by the normal force, which would be 804 newtons divided by 1,340 newtons. You can see that newtons cancels, making the coefficient of friction mu a unitless decimal. Take a second to put that in your calculator. And you should have gotten about 0.6. Number 5. At an applied force of 530 newtons, the boulder just began to slide. Assuming a coefficient of friction of 0.65, how much did the boulder weigh? So we're looking for the weight this time. Okay, that's our thing. Now, keep in mind, normal force balances weight. We were given an applied force of 530 newtons, which, by the way, is the same as the friction pulling the other way. Okay, and we were given mu. Okay, we were also given mu in this problem at 0.65, so we were given that too. So again, we need normal force as weight, and we also need the fact that friction is the same as the applied force, and that's going to be equal to mu times the normal force. Okay, so my thinking is figure out what the normal force is, and the normal force balances the weight. You'll be able to figure out the weight. So friction equals mu times normal force. Solve for normal force. And it's going to be, we have to divide both sides by mu. Okay, the friction force is the same as the applied force, right? Because we're balanced. So 530 newtons divided by your mu, which was 0.65, and the normal force, which is the same as the weight, And that's what we're looking for. Go ahead and plug that into your calculator. You should find a boulder weighs about 815 newtons. Okay, in the next part, we're going to be focusing on sliding or kinetic friction. So sliding friction, same thing as kinetic friction. So in the first set of examples, we were looking at the force required to get something going. Now we're going to focus on the force while something is in, again, assumed to be constant velocity motion, but we have actual movement here among a rough surface. So back to that question with the pile of leaves, okay? So that pile of leaves still weighs 80 newtons, okay? Still weighs, I said 80, my apologies. It weighs 580 newtons still, which means the normal force still balances the weight. Okay, and since we're moving it at a constant velocity, the force to move it still equals friction. Okay, now it says the family estimated that they were applying 93 newtons of force, which would be the same as the friction here. So normal force balances the weight, applied force balances the friction, which equals mu times normal force. We're solving for the coefficient of friction, which would be mu. Okay, so friction is equal to mu times normal force. To solve for mu, you have to divide both sides by normal force. So mu equals F over N. Okay, the friction force, sorry, I kind of jumped the gun there a little bit. There we go. The friction force is the same as the force the family is pushing, so that would be 93 newtons. The normal force is the same as the weight, your 580 newtons. And so the force to keep this moving, okay, excuse me, not the force to keep moving. The force to keep it moving would be the 93 newtons. At a constant speed. And if you divide that by 580, we get 0.16. Now, one thing to notice, if we look at this question while the bag of leaves is moving, compared to number one, when the bag of leaves was not moving and it was harder to move, it had a much higher coefficient of friction. And more force was required to move it. So it took 319 newtons just to get it to move. It took only 93 newtons to keep it moving at a constant speed. Okay, so what does that mean in plain English? It is harder to get something moving at first, but once you do, there's less force required to keep it moving. Number 7. Aboard the sled, Timmy kicked off with his feet, and although it wasn't easy, Lassie was able to pull the combined 490 newton weight of sled and Timmy. Assuming the sliding coefficient of friction is 0.05, how much force was Lassie able to apply to the sled? Okay, so that is our question mark. Okay, the total weight of the sled, still 490 newtons. Normal force still equals weight, and force still balances friction. I hope you're seeing the consistency in the problems we're doing. Now, how am I going to find the force? Well, that's easy. Find the friction because they balance each other, and mu times normal force would be that. So my applied force would be the same as my friction, which is mu times normal force. Okay, we were given the mu at 0.05. That's our coefficient of friction right there. And the normal force was the same as the weight, right? Your 490 newtons. Everybody, please take a moment to put that in your calculator, and let's see how much force the dog is pulling Timmy and sled. Okay, if you did this right, you should have gotten about 24.5 newtons. Okay, number 8. The children had been splashing all day in the pool. Their father was surprised that he could drag the plastic wading pool over wet grass if he gave it a jerk to get it started. Assuming the coefficient of sliding friction is now 0.08, how much force must he apply to a 4,050 pool once it is moving? Okay, there's our picture. Again, we're looking for force. That's our question mark. Again, the wading pool weighs 4,050 newtons, which is the same as your normal force. And again, applied force balances friction. Okay, so we're looking for force, which is the same as friction, which is equal to mu times normal force. Mu in this situation is 0.08. There's our mu. And the normal force is the same as the weight, which is 4,050 newtons. Multiplying those two, you should get about 324 newtons is the amount of force that the father applied on the pool. And finally, ladies and gentlemen, number 9. The boys were relieved to find that the 1,340 Newton car was easier to push once it got going. Just how hard did they have to push, assuming a coefficient of friction of 0.4? I hope you see why I'm just copying and pasting the same picture over and over. We had a 1,340 Newton car. Normal force balances weight. Applied force balances friction. Okay, and we're looking for how hard they had to push. So that would be our applied force. Okay, we're looking for how far they pushed. So that equals friction, which is mu times normal force, and normal force balances weight. So applied force balances friction, which is equal to mu times normal force. Plugging in, we have a mu of 0.4. There's our coefficient of friction mu. And we have a normal force, which is the same as the weight, of 1,340 newtons. Please take a second to plug that in your calculator. You should have gotten about 536 newtons. I hope you found this video tutorial to be helpful. Pause and rewind as you need to. Thank you. See you next time.